Okay, so we are going to finish the first section of chapter 3. Try to finish the second section today, and then tomorrow we can just blaze through the whole practice quiz, have time to do homework, etc. Awesome. So, we were talking about, let's do a little review of what we did last time. So we graphed some functions, right? We graphed some functions. They are exponential. They're growing. We have asymptotes, etc. Hopefully you remember this from Algebra 2. Exponential growth and decay. So you can figure out how much money you're going to make if you have a savings account, depending on how many times it's compounded. So maybe you buy some stocks and they're compounded quarterly, right? You get your dividends, you get your money back that you invested. So here n is the number of times per year, t is the time in years, r is the rate. But what's the tricky part about r? What do you have to remember? Decimal. Switch from percent to decimal. Okay, I just listened to Miss Rotter be sad that her student who is taking a test in this forgot to switch it. Alright, so 7.2%, you have to put 0.072. This is where people make the mistake, right? They don't move the decimal place over. It's the most common mistake. All right, so this is compounded at certain increments versus if we wanted to continuously compound. So we went over like, okay, well, you know, if this woman invested $2,000 when this baby was born, you know, how much money would she have if it was every, quarter? You get the interest. Okay, how about every month? You get the interest. How about every day? You get the interest. So then the difference is the more often you compound, you get interest on top of the interest that you charged. And then you get interest on the interest on the interest. Like it just rolls along. So it's great if this is in your benefit and you're making money, but it sucks if you are the person who has the money being sucked out of them like a vampire. Okay, so
Are college loans compounding continuously?
It is continuously. Yep. Now we're going to talk about this. So, yeah. I will not go off on the tangent like I did last time. Okay, focusing. Yes, I have very strong opinions. Okay, so continuous compounding interest formula. APERT, have you remember APERT? Yeah, A equals P E to the RT. So R rate, but in decimal. So if it's 5%, you can't just write 5. 0.05. Okay, my hope is I pound this into your brain so you will not make that mistake, and it will be great because it's like a dumb place to make a mistake, because sometimes it's so easy, you like start going fast and you forget about it. So I'm trying to help you remember. This is going to be in decimal, so it's just a rate. T is the time in years. Oh my gosh, I don't know why I can't write right now. And then P is your principal, how much you start out with. So it's roughly the same as up above. The difference is our base is E, 2.712 or whatever it is. Okay, so let's say the same woman invested same amount of money, $2,000, in the 5% imaginary, I don't know who she bribed to get that percentage rate, but instead it was compounded continuously. So here, this is the key to knowing which one to use. If it says compounded continuously, or if it's like quarterly, monthly, like it will be an English word, right? It's not always going to tell you like N is 4. Like no, kind of have to digest the words. Okay, and then what will her account balance be after 18 years? Okay, so we know our rate is 0.05. We have P, the principal amount we started out with is 2,000. Time is 18. Fill it in. A equals P times E to the RT. Okay, so I made sure to leave these up here. We can compare the money values, right? So if it's just once a quarter, right, this much money. And then if it's every month, okay, that's about 20 more bucks. And then if instead of quarterly, it's daily, that's about $30 more. And then if it's not just daily, it's continuously. Literally, this is, it's only, 31 cents? But still, that's 31 cents. It's only, you only start with $2,000, And at 5% interest rate? Yeah, right. The federal government, I believe, for one of the type of loans is like, you could take $9,500 out at an interest rate of 6.8%. And the difference between subsidized and unsubsidized, do we have an idea what the two mean? So if you subsidize, that means like, okay, we will pool our money together and more or less like, that's not a good explanation. So subsidized is the government will pay the interest for you while you're in school. Unsubsidized, guess what? Interest accrues, and then after 4 years, when you start paying your loans after college graduation, guess what? Not only do you have the $9,000 that you originally took out, you have all the interest that accrued over 4 years at 6.8% interest.
That kind of sucks.
Yeah, okay, cool. So that's kind of the idea. I want to make you guys aware, right? We're gonna, so Charles Gambino, stay woke, let's do this. It just makes me so mad.
Well, like, how do people get through college if they don't take out loans? Like,
people have parents that pay, or parents that like will have a savings account for them. Because I worked through college. I worked like 20 hours a week. So I still have to take out loans. Just sucks. Also, some colleges, if you have scholarships, they'll actually give you it, not just take away. They won't just be like, oh, yeah, you got $10,000 scholarship. I'm going to subtract that from the scholarship we're giving you. So, also, most people probably only have like 2 parents for income. So that's a little different. Because they look at me and they see 4. But every single cent of my student loans was supposed to be parental contribution. You know, because apparently people have parents that do things for them. I don't understand at all. Okay, let's change the problem a little bit. So 2,000, let's make it 3, yeah? She gets a little crazy. You know, maybe that bris money, yeah? Yeah, right, bris? No. Yeah, bris? You know,
it's like when you're born.
Exactly. So, you know, all these people come to the bris and they're like, you know what, let's have this person get some money, you know, let's have the baby get some money. Whatever. I'm trying to justify why we're increasing from 2,000 to 3,000. Right? Old grandma, grandpa came through and they're like, let's add 1,000 for college fund. Okay, you know what? We're going to keep the same rate, right? So, still, this imaginary 5% savings plan. This time, let's have it be 20 years. You know, just 2 years longer. Let's see what will happen. Let's see what will happen. So, A equals 3,000 e to 0.05 times 20. Okay, before we put it in our calculator, I mean, it's not, do we think it's going to be that much more as, you know, $4,900? We start out with $1,000 more, but it's the same interest rate. It's very close to the same years, right? 18, 20, very close. How much do you think it's going to be? Do we have a guess? 6,000? 7,000? Okay. If you plug it in, guess what you get? $8,154.83. Significantly more. Significantly more. Should we make this a more realistic number? Do you want to do one more? Let's do something like I was just talking about. Let's have the principal be, let's make it 10,000, right? I'm pretty sure it's like 9,500 for, but let's make it simple. Let's do 10,000. Let's do the real interest rate of 0.068%. Thanks, government. And let's see, let's do time is 14 years, right? Because 4 years to get through college, right? Let's say this is the loan you get your freshman year. It's unsubsidized, right? It collects interest as you're going through school. And then you do the standard repayment plan, which is 10 years, right? Some people do the, income base, which takes, 20, 30 years, where you pay a certain percent of your income. Yeah, servitude. Okay, so let's see how much money this amounts to. Right, so I did 14 years because, you'll be in school for 4 years. This could be the loan you took out your freshman year. And then the 10-year repayment plan. Let's see how much money you actually had to pay by the end or so. This is roughly. Yeah. You're right. I put 1,000. I meant 10. Did you put it in?
Yeah.
What'd you get?
25,908.86.
Yeah, exactly.
That really adds 15 grand.
Yeah. this is, if you do the standard repayment plan, you're probably going to pay double the amount that what you borrowed. This is how they make their money. That's my goal. I want you guys to see the craziness of it. All right, this is my conspiracy, tin hat theory. This is like, what do I want you to learn from my class? Be a nice human. Don't give up when you see hard problems. And student loans are crazy. So there you go. This is why we have a student debt crisis. Because welcome. If you pay the minimum amount, oh yeah, you're just gonna be paying interest for the first 3 years of your loan. It's not gonna be paying down the principal, just the interest. So this is not. This is actually a very realistic number. So.
Doesn't interest just continue increasing also at the same time as paying interest?
The amount that you have interest. The interest rate doesn't change, but the interest, oh yeah, of course. Because it's like, oh, after 1 month, this is how much money you have. Okay, guess what? Charge interest on it. Well, so you charge interest on the interest. And then it just keeps growing. So, even if you go bankrupt, student loans don't disappear. Even if you die, they will chase down your kid. It's literally shackles. The income-based repayment plan. Oh, guess what? All of a sudden you get a good job. No, you signed that away. You have to pay that certain percent. Yeah, it's hard to change plans once you're in one. So just me, paying double the amount that I need. So just me paying $250 extra on one of my loans. I'm gonna pay it off 3 years early, and I'm gonna save at least $10,000 of interest. It's crazy. So this is why I grind, because think of that. It's like $15,000. Could travel the world for 6 months with that price, Okay, so hopefully if you see that, if you don't have to do student loans, literally your mom, dad, grandpa, whoever's giving you that money, you gotta tell them you love them a lot, because that is crazy, right? It saves you a lot of stress and a lot of bitterness and resentment that you don't need in your life. So, in addition to investments, populations of people, animals, bacteria, and amounts of radioactive material can also change at an exponential rate. So, this is for people, animals, bacteria, things that have a single number, right? You can't have half a person, right? I know, you'll fight me on it, right? What if someone doesn't have legs? Whatever. That's not what I want. I'm just saying, you do a problem on your homework, 200.5 people. No, 201. Round to their nearest number. You guys know how to round. Okay, so what would happen if I go up to this equation and I put 1 for n, right? I have an annual rate. What would this turn into if n was equal to 1? Yeah, to the t. Okay. Look at the page we're on, not this one. The one in this matches exactly. Okay, so it's this is where it comes from. There's not, 5 different equations. They all are roughly alike. Okay, this is if n is equal to 1, right? You have an annual rate. R, once again, is your rate, and you have to have it in decimal form. So if you think about it, a growth rate means positive, a decay rate is negative because it's getting smaller. So far, we've only talked about money. Yay, and money is always growing, whether that's good for you or bad for you, depending on which side you're on. But if we have things that are slowing down, right? Like the population of the world, roughly it looks like an exponential right now. It's going straight up. A little morbid. There's a virus going on right now. Maybe this is our carrying capacity, right? This is when so that every year they go out and they count how many deer there are in Nebraska. They roughly estimate to see how many permits they'll let hunters shoot deer. Okay, so what if they didn't put out enough permits and all of a sudden there's lots and lots of deer? That amount of land can't support that amount of deer, so there's disease and they die out. Once your population gets so high, the carrying capacity, it starts dying out, right? It starts flattening out. This is not flattening out. This is just purely exponential growth, exponential decay. Okay. So we could have a decay, right? Things are dying off. So for instance, there's Pablo Escobar's hippos right now in Colombia are wreaking havoc on the ecosystem. Because he had 4, right? Once his house, whatever. They donated all the hippos to the zoo except 4 of them, and now there's over 80 hippos. And their poop is so bad that it's making the lake toxic and having algae blooms. So we could talk about the growth of algae in these ponds, which is going to be exponential, or we can talk about the fish that are exponentially dying off because of these toxic waste. Okay, so, and then continuously, so if you have something that's like just like things, right? Bacteria, people use the left one. But for instance, you could use the right one for like half-life. So I've used this in my life. I went to India, did geology research. You can figure out where, like this piece of land I am standing on right now, I can dig in, find a rock. There's these crystals in the rock called zircons, which have uranium in them. You crush the crystals. You see the ratio between uranium and its first like decomposition, right? What it goes into. So based on the ratio, you can see where in the half-life curve you are and how long ago this rock like was frozen in time. Also in the same rock, you can see these like almost like a magnet, right? You can see which way the magnetic poles are aligned in the iron that's in the rock. So based on that, we know how old the rock will be based on the half-life. And then based on which way the poles are pointing, we can see, okay, like where was it on the Earth at what time? Anyway, that's more or less like where this is coming from. I don't want to go in too much depth, but I think it's cool. All right, it states population is declining. Wait, declining, positive or negative? One more time. Negative, declining, going down at 2.6 annually. Perfect. This is literally N is 1. The state currently has a population of approximately 11 million people. If it continues to decline at this rate, predict the population in 15 and 30 years. Let's go to the first. First, A, 15 years. We want to know what is the final population. We have the initial population, it's 11, million. I don't want to type in all those zeros, so I'll put everything in terms of million. So our answer at the end will be in terms of million. We have a rate, right, negative 0.026 for A. Our time is 15 years. So if we plug everything in, 11 times 1 minus 0.026 to the 15 years. So it's just 11 times 0.974 to the 15. So this is approximately 7.4 million. So remember we approximated the original to be 11. So this will be approximately 7.4. And we're in terms of million. Okay, so after 15 years we went down, 3.6 million? Okay, so we're about 2/3 of where we started out with, right? Literally 1/3 of our population, 1/3, done, gone. So in real world, Japan is dealing with this. America is going to really have to deal with this in the next 15, 20 years. The declining age of our population, right? We're having more and more people live longer, be older. So it's hard to have all the care and take care of them. Right? A declining birth rate also, right? We have less new people. We have this large group of the baby boomers. Okay, so think about it. What's our estimation? How much do you think will be after 30 years? 1, 2, 3, 15? Has to be less than 7.4. But in the first 15 years, we declined 3.6 million. Right? Are we going to decline another 3.6, or is it going to slow down? Yeah, it's going to slow down, right? So if you think about exponential decay, at first, it really decreases and then it flattens out, decreases at smaller and smaller rates. So kind of trying to have a grasp of what our answer should be. You can see if it makes sense, because that tells you if you plugged it in right or not. So really the only thing we're changing is this time the years is 30. All right, we have the same initial population. We have the same decline rate. It's just for 30 years instead. So N is approximately 5 million. Okay, so in the first...
I actually guessed that.
Yeah? That's good. That's good. First 15 years, down by 3.6 million. Next 15, down by 2.4, right? So the amount we're decreasing gets smaller and smaller and smaller. Okay. Perfect. And we can go on to section 2. So once we learn section 2, Like, we can go back and do more with these equations. I could tell you how much I end with. I could change what I'm looking for. For instance, a hard problem would be, how much do I start with? If I tell you how much we end with, the population, etc., like, you have to manipulate the variables and solve it. Okay, so I gave you a study guide, which is more examples, but we're going to go to 3.2, which is page 10. And hopefully this will be, like, hope we remember part of this, but also cool, ready to teach. All right, so if 2 to the first is 2, and 2 squared is 4, and 2 to the third is 8 power, here, I'm wanting to know 2 to what power is equal to 6. So if we think about it in terms of exponents, right, 2 to the first power is just 2. 2 squared is just 2 times 2. 2 to the third power is 2 times 2 times 2. So the hard part is, this question mark here, it's got to be a number between 2 and 3, right? Because 2 squared is 4 and 2 cubed is 8. So 2 to some power between 2 and 3 will be 6. So to answer this question, we need a logarithm, right? 2 to the base, 2 to what power is 6? So 2 to what power is 6? Literally, this is how we write it. 2 to what power is 6? Logarithmic form versus exponential form. So normally when we would write it, we would say, okay, log base 2 of 6 is equal to y. Right? That's how you would say it. Log base 2 of 6 is y, right? Reading across. And then to write it, you do 2 to the, on the equal sign, little swoop-de-loop. Do you guys ever do those? Have you seen that before? I'm not really speaking English right now. So you do 2 to the y is equal to 6. 2 to the y is equal to 6. We're trying to solve for what y would be. So more or less, what I'm trying to show you is this next part, right? Relating log and exponential forms, right? So we have a base b, our exponent is y, and then x is like what it is equal to. So you always go b to the y is equal to whatever's inside. So this is literally just b to the y is equal to x. And the way you say it is log base b of x is y. And on the right side, b raised to the power of y is x. This is how you would talk about it. B raised to power of y is x. Did you guys remember these? Because if not, this is on like your 100 topics of Alex. So all the 100 topics are literally what we're doing. I say this quarter, I forgot the quarter ends beginning of March. I have it going until seniors leave. Like, that to me is end of third quarter, because normally that's when it coincides. So before spring break, right? This is everything before spring break, everything seniors will learn. All right, so you may have forgotten this, but we're like taking it from square one again. So some basic properties of logarithms. Can I zoom in? Are we good to write this? Wonderful. Okay, so remember the little circle, the way we would write it? So I'd say b to the 0 power is 1. Oh, okay, that's all it is. So log base b to 1 is always going to be equal to 0. So it doesn't matter what your base is, log base anything of 1 is always going to be equal to 0. Because the only exponent that would make any number equal to 1 is 0. Okay. And if you have the log base b of b, literally the same number right here, it's going to be 1. More or less, it's like effectively canceling itself out, right? B to the first power is b. Anything to the first power is itself. Surprise? Okay. How about this next one? Okay. So if we do the little, I don't want to call it a swoop-de-doop, circular way of converting between log and exponential. Okay. B to the x is equal to b to the x. Wait, what? That's crazy. So what that means is I could literally cross out b, log base b and b, and then we'll get the same thing. If you are, oh my god, what's a better way to say this? log base of the same base to an exponent, well, that whatever that exponent is what the answer will be. So example, if I have log base 2 of 2 to the third power, what is this equal to? It's just equal to 3, right? Because log base 2 and then you have the same power. What? You got it? Yeah, you did. Heck yeah. Another way to think about this, right? 2 to the y is equal to 2 to the third. Oh, literally all that, in order for that to be equal, the exponents have to match. Okay, that's a property. And then lastly, b to the log base b of x is just going to be equal to x as long as x is greater than 1. Okay, because if you think about this, if we have like 2 to the log base 2 of x, what this effectively means is, okay, 2 to the y power is equal to x. 2 to the y power is equal to x. So then I want 2 to that power, so 2 to the x. Effectively, if you have a base raised to log of the same base, those two effectively cancel each other out, and we're left with the exponent. So these two effectively cancel out. Where this is going to be useful, are you ready? This is where you're going to see it. If I have e to the ln of x, do we know what ln is?
Isn't it e?
Log base e. Wait, if we have e to log base e, oh, those go away and we're left with x. This is where it's going to come in handy. You know, surprise, that's a spoiler. You know, didn't really tell you this yet, but I want to make sure I'm showing you at the beginning, like, where you will see it. Yeah, that way it's in your brain. Okay, so what else is important that I have to tell you? Should I wait for this? No. Okay, if I have something like square root of x, what is the exponent? 1/2. If I have cube root of x, what is the exponent? 1/3. 4th root of x, 1/4. 5th root of x. Okay, those are the exponents. All right, cool. So we're good there. Let's go through and let's evaluate each logarithm. So in order to do this, it's good to convert to exponential form. Okay, so I'll say equals y, so 2 to the y is equal to 16. 2 to the power of y is equal to 16. Aye. So 2 to the power is equal to 16. Ideally, right, so you know off the bat what power this should be. But if we hit a problem that's harder, that you don't know what it is, what you would like to do is use some of the properties we used up above. So if we could write 16 in terms of 2 to some power, then we could set the exponents equal to each other. So 16 is just 2 to what power?
4.
Exactly, right? 2 to the 4th power, and then since I have the same base on both sides, and it's equal in between them, right? There's an equal sign between them, so we know it's equal. That means if the bases are the same, the exponents must be equal as well. So we see y is 4. So keep in mind, in order to solve these logs, we just convert it into exponential form. Yeah. It's loading. Okay. Second way of doing this, you could say log base 2. And instead of saying 16, we could say 2 to the 4th. Well, if you have the base, if the base you're going, whatever base, right, log base you're in, if you have that same number as the, yeah. So that's why it cancels out and we're left with 4 equals y. Right, so you have log base 2 of 2 to the 4th. Oh, literally, the base I'm taking, I have in my, like, what I'm trying to take log of. Since those will cancel, we're left with just the exponent. All right, let's try the next one. Let's try the next one. So, right, I'm going to write it as 5 to the y power is equal to 1 over 125. Ooh. It would be great to rewrite it in terms of, 5 to some power, yes? Okay, so I have 5 to the y, and technically 1 over 125 is the same thing as 1 over 5 to the 3rd. Right, because 5 times 5 times 5 is 125. So instead I could write the right side as 5 to the negative 3. Beautiful. Because remember, if it's on the bottom of the fraction, you can just make the negative, exponent negative and then move it to the top. Okay, so that just means y is -3. All right, how are we doing so far? Coolio, try out C. Try out C. Okay. We solve C? All right, let's try D. Try out D if you haven't already. You guys try E already? I'm going to add an F. No, wait, I already added it. Never mind. It's exactly the same problem. So 22 to the power of log 22, you're just left with what the exponent is. Because if you have b to log base b of x, it's just going to be equal to x. All right, how do we feel about this first page? So square root of 3 is the same thing as 3 to the 1/2 power. Because the square root is to the 1/2 power. Yeah. So I tried showing you guys, like, remember when I was asking what the exponents were up here? Yeah. I was trying to, like, make sure we were good with it before I set you off. But I didn't want to make it too obvious, so I asked for it first. Hello.
Hi.
Cool. Did you get them all signed up?
Yeah.
Ooh. All right. Is Frankie or Robert in your class?
No.
Okay, cool. Okay. Cool. All right. Now we're going to talk about common logs. So the properties, like, we just used basic properties. Now we're going to talk about specifically of the common log. So common log is base 10. Natural log is base E, right? And so before we had these fancy TI Inspire calculators, those were the only two bases you could use on your calculator, and you'd have to go through and use a change of base equation. But lucky for you, your calculator allows you to use any base. You could literally use pi as the base. It does the change of log for you. And that is very, very powerful. Like, I know it means nothing to you, but this is crazy. This is a lot. So, basic properties of common logs. Guess what? If it's a common log, you don't see the base. Secretly, it's base 10. So if it's ever just, oh, log blah, 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 it doesn't have the base written, it's secretly going to be 10. Okay. So we have 10 to the 0 is equal to 1. And then here, 10 to the first power is equal to 10. We're just using the circular motion, little curly curl action, right? Because here, this is secretly base 10 to the x is equal to 10 to the x. So you set the exponents equal. Oh, literally, if you have the same base and then that base to an exponent, they'll cancel out. Similarly, this is technically log base 10. So the issue is all that I made different was, oh, this isn't a single base. It's all base 10, and I don't write what the base is. If it's not written, you assume it is 10. Same way, if I just write x, you assume the exponent is 1, right? If it's not written for log, we assume the base is 10. So keep in mind, log functions are undefined for negative numbers. You cannot put in a negative number, right? So if you're trying to take log base 10 of -2, right? 10 to what power is -2? Think of a number. What's 10? 10 to what power is negative 2? It can't be, right? That's what it means by can't take logs of negative numbers. Because there's no exponent, right? If I pick a really, really, really small y, like negative 1,000,000, okay, well, that just is 10 to 1 over 10 to 1,000,000, so it's still going to be positive. That's why we have an asymptote at the x-axis, and everything's above it. So you can't take a log of a negative number. So these are like the two important notes here, right? Base is 10 for a common log, and log functions are undefined for negative numbers. So I'm telling you the trick right now. If I try to make you do log of a negative number, you can't do it. Don't be tricked. Log functions are undefined for negative numbers. Okay. Evaluate each logarithm. Do you guys want to give these a shot yourself first? No, yeah, okay. Try out A, try out A. Yeah, try out A. So remember, not written, we assume it's 10. Do a little swirl action. 10 to the y is equal to 10,000. Now this would be great to write in terms of 10 to some power. If you count how many zeros, that is what power 10 is raised to. 10 to what power? Oh, 1, 2, 3, 4 zeros, so 10 to the 4th power. So we see y is equal to 4. Another way to think about this, if you have log, oh my god, why is it not writing? We have log base 10 of 10,000. Well, you can just write that as log base 10 of 10 to the 4. You have the same base, and then the base raised to an exponent. It's just going to be whatever the exponent was. So that's the second way of solving. I like this left way. It just is very methodical, very clear. How about the next one? What will it be equal to? What's b? 12, right? Because technically this is log base 10 of 12. Perfect. How about d? How about d? Log, it's secretly base 10 of negative 12. Not positive. No real solution. All right, no solution. Can't take log of a negative number. And lastly, log base 10 of 14. Yep, it's part C. So secretly there's a 10 here, equals y. Now 10 to what power is equal to 14. So this is where the calculator comes into play. Because there's no way you could solve this like on your own. I mean, you could, but it might take you a while. Right? Because 10 to the first power is 10. 10 squared, right, to the second power is 100. So it's going to be between 1 and 2. Because 10 to the first is 10. 10 squared is 100. So between 1 and 2. So you could say, you literally could write log 14. Do you guys see the log button on your calculator? Maybe. It literally says, it's on top of the 10 to the x button. It's in blue, so you have to push control 10 to the x. To a couple places. So log, you don't necessarily have to put in the 10, so if I put 14, I see you get 1.14613. So we'll just say round to the nearest hundredth, 1.15. 1.15. So y is 1.15. Cool. That's the common log, base 10, and now natural log, which is base e. Right? A natural log with base e, literally it's log base e. Instead of saying log base e, they just say ln, because that's natural log. So we always just write this as ln, and that's natural log.
Why did the number e come out?
So it is the solution to this limit up here. Right here. This guy. That's what it's defined to be. Because the issue is as x gets bigger, the second term goes to 0, but then, any number times itself over and over again is going to be getting big. So any number larger than 1, if you multiply by itself again and again and again, it's going to grow. But I'm also getting closer and closer to 1 as x gets bigger. My 1 over x gets smaller and approaches 0. So it's a fighting contrast. You know, who's going to win at the end? If a number is really, really, really big, it's going to basically be 1 to that power. But it's not going to be exactly 1. It'll be like 1.0000001. Right? So it's just a fighting contrast between these two. So you could, there's a lot of content out there just about Euler. What E is, I think deals with Euler. Did I write on this page? Don't want writing on there. Don't want to save it. Okay. Is there writing up here? No. Okay. Keep going down. Ooh, sorry if this is motion sickness. Natural log. Same rules as before. It's just the difference is it's base E. So let's go ahead and let's try these out. So keep in mind, x has to be greater than 0. Also important, ln and e are inverses. Because if you plug a function into its inverse, they more or less cancel each other out and you just get x as the answer. Remember when we did that in section 7, chapter 1? Yeah. If I take e to the ln of a number, like in C, e to the ln, you just get what the exponent is, and that's 4. If you take ln of e to the 4.5, okay, well, technically this is log base e. Ln of e, those cancel out, and I'm left with just what the exponent was. So this guy is from here, and this one is for here. Ln of a -2, well, no real solutions. You can't take log of a negative number. And ln of 7. Okay, so then this is where our calculator comes into play. So above the e to the x button, do you see the e to the x? It's left of the 1 number key. It's the very left, it's e to the x. You push control, and the ln is on top of it, and then you just plug it in. Wonderful. So we get e to the 7 is equal to, e to the y is equal to 7. Because this is technically log base e of 7. Because ln is the same thing as log base e. So you get y is, what is it, 1.8? 1.9? 0.946. Cool. Okay. So you could, like, depending on rounding, 1.9. Sorry. Okay. So now graphs 1, 2, 3. 3 pages. Wonderful. So if you think about the exponential graph, right? The graph of the e. Let me go up here where we had it. Nope, that's not e. I just want to show you the graph. Okay. So let's see. 1, 2.7, 7.4. So it looks something like this. Okay, this is the graph of e to the x. And so I'm trying to introduce you, like, naturally to log equations. So if ln, the natural log, and e, the exponential function, are inverses, what does that mean graphically? So you don't have to draw this. This is on, like, I went up to page 4 because I want you guys to understand what we're doing before I go on the notes. So you don't have to write this down. I just want to make sure you're clear. Because I'm going to go back to where we were, and I'm going to use that graph. Okay, what does it mean to be inverses? What's it mean to be an inverse? Huh? Opposite, because they are reflections over the y equals x axis. So inverses literally are reflected across the y equals x axis. So I draw this axis for you. So wait, what used to be x comma y is now a y comma x. So where I used to have a point at 0 comma 1, now I'll have a point at 1 comma 0. So at 1 comma 0 right here. And where I used to have an asymptote at y equals 0, Now my asymptote is where? X equals 0. Now I have an asymptote at x equals 0. So my asymptote goes up like this versus my asymptote that was like this. Okay, let's take a couple more points. So notice that as I go to the left with my exponential, right, it drops down and gets closer and closer to the x-axis. So here this guy has a point.
Consider increasing or decreasing?
Where?
The exponential one, would that be a growth or decay?
E to the x is growth because e is greater than 1. E is 2.7. Yeah. So if I wanted to take this blue guy and flip it over the y equals x axis, it would roughly look like that. Kind of close, right? So take your head, put it at a 45-degree angle. Kind of looks like they are mirror images of each other. I'm not a perfect artist, but it's close, right? It's close. Because you follow the axis and swoosh. Follow the axis and swoosh. Yeah, exactly. Flipping it over here. So blue, if I flip it over, it should be the green. There you go. So if I take 2 to the x power, right? If I do that exponential, I think that was one of the first ones we did. Cool, you could graph that and then flip it over the x-axis. But there's like easier ways of doing it. But I just want to make sure you like see where this is coming from, because literally log is the inverse of whatever the base is. It's just flipped over the y equals x axis. Okay, go all the way down to the graphs. Because now we're going to graph logarithms. So more or less, I'm going to draw what I just did. Right? If we have the y equals x line, remember it comes from the exponential, right? Y equals b to the x. And so that means this one is just going to be log base b of x equals y. Not too bad. It'd be, the easiest way is to convert the log function into an exponential and then graph it that way. So we could have logarithmic growth, right? As you go left to right, the y values are getting bigger. Or you could have logarithmic decay. As you go left to right, the y values are getting smaller. Notice the asymptote is the y-axis. So think about the exponential functions, the domain was all real numbers. So now the log function, the range is all real numbers. Okay, for an exponential, the range was 0 to infinity. For a log, the domain is 0 to infinity, right? So everything is like flipping because it's inverses. Maybe I should write that out for you. Okay, so b to the x, the domain was negative infinity to infinity, and the range was 0 to infinity. This is for inverses. Inverse functions. Because I don't want you to have to memorize like a billion, cajillion things. Like if you understand where it's coming from, it should be easier. What was your question?
Oh, couldn't you also have a base that's a negative number?
No, because the negative number, I think we went over it last time, it like flips back and forth. Like literally to be an exponential function, it has to be greater than 0. It can't be 1. That was on the first page of the notes. Talking about exponential functions. The base is constant, exponent's a variable. The base has to be greater than 0. Yeah.
But the y is not.
So if you type it into your calculator, like negative 2 to the x power, it looks like a, you know, the gramophone, like the Grammys and the things that used to play records? Literally, it's not just one line, it's like 2 lines filled in between. Because if you take negative 2 times itself, you get 4 times negative 2, 8 times negative 2, negative 16, 32, negative 64. Like it keeps going back and forth. It's not a nice, smooth function. Yeah, I can put.
What about the numbers in between, like 2, I don't know,
Yeah,
2.5?
that's why it's literally filled in all together. I'll show you on the calculator what it looks like. I forget if I did it for this class or the other one. I know I did it. So cool. Okay. Okay, so it's a good question. This is why we define exponential functions as having a positive base. Looks kind of crazy. What else do I want to talk about? So we're gonna, yeah, we have some functions to graph. Give me a moment though. Come on. Okay, let's add graphs. So easiest one, let's do like 2 to the x, right? That's a nice exponential function. There we go. Okay, now I'm going to do -2 to the x power. Because it just flips back and forth. Yeah, so let me zoom in on it. Because it's technically going to be solid red, but your calculator won't show you that because it's like freaking out right now. If the calculator had, you know, if I'm personifying it, it'd literally be freaking out right now. You're like, what are you doing? Why are you doing this to me? Oh my God, it's crazy. Let's zoom in. Let's see how far we can zoom in. It's just going to feel more and more, it's just going to get more and more solid.
You can't have more than like the y value for an x value.
Exactly. It's,
Right.
yeah.
So it can't be all red.
I mean, it's just, okay, so, you know, 2.01 versus 2.001 versus 2.00001, like, there's so many minuscule little steps you can take where it's, like, not technically the same y value, but, yeah. This is why we don't have it, this is why we don't have the base as a negative, because that's something else. Okay. Hopefully, this helps. Okay, cool. Because that's nasty looking. What else do I want to show you guys? Yeah, it's cool. It is, yeah. Yeah. Okay, let's keep going. I don't know if I don't really want to get into too much of that right now. All right, log base b of x. So, we're talking about the log function. The log function's domain is 0 to infinity, and its range is all real numbers, right? Because the log function starts down, and then it just like keeps, it's increasing, goes on forever up. But notice it cannot cross the x equals 0 axis, because that's where its asymptote is. Inverse functions, the domain and range switch for each other. Okay, so example 3, we're going to graph and analyze each function. So we have f of x equals log base 2 of x. So there's 2 different methods I'm going to show you. Perfect. So this is method 1, right? We're going to rewrite in terms of the exponential function. So do the little loopy curl. 2 to the y power is equal to x. So since we're not shifting our log function up or down, we're like not going to be switching where our asymptote is, right? We're not going to be moving left or right, so we're not moving where our asymptote is. Our asymptote is going to be at the y-axis, or x equals 0. Did you guys graph log functions last year? No, but you graphed exponential. Yeah? Exponential functions last year? Maybe. That's all, okay, that's fine, because we're going to do it now. So, we're going to use the exponential function that we rewrote, and I picked some numbers for you. So we have 2 to the y power is equal to x. Here my x is 1/2 power. So 2 to what power is equal to 1/2? Right. This is just going to be 2 to the -1 power, so the y is -1. Okay. 2 to the y power is equal to 1/4. Well, 1/4 is just going to be 2 to the -2. It should probably be switched. Because, you know, I was trying to go in order of my y values. Whatever, my bad. Okay, so this first method is we are solving for the exponent, but we're picking the nice numbers that are all base 2. Like 2 to the y power is equal to 1. Well, the only y power, you know, is going to be 0. 2 to the 0 is 1. The only power that has a number... The only power you can put any number to where therefore it'd be equal to 1 is the 0 exponent. Okay, 2 to the y is equal to 2. Okay, so that's just going to be 2 to the first. And 2 to the y is equal to 4, so that's just 2 squared. So I have solid y values, right? Integer y values. My x is, 1/4, 1/2, but we can deal with that. So at 1/2, we are, at 1/2, we are at -1. So that's about right here. And at 1/4, we are at -2. Let's see, we have a point at 1, 0, point at 2, 1, and a point at 4, 2. We know we have an asymptote at y equals 0, aka the y-axis. At x equals 0, aka the y-axis. I think I said that backwards. So notice I'm connecting my dots and I'm extending my graph all the way to the ends, right? I didn't just draw it to be 1 centimeter long. I extended to the ends because it is a function that just keeps going and going. So you can see my individual points I wrote. All right, so I think we have enough people. I'll just go around. So first, domain. Let's start with Chelsea. What's the domain of this function? What's the domain? The x values.
0 to infinity?
Yeah. Why did I not write a square bracket around 0? Yeah, I'm not touching 0. There's an asymptote at 0. Exactly. Range, D, what's the range here? Exactly. So I can pick larger and larger and larger numbers, right? Larger x values, and the y is just going to keep increasing. And then since I have an asymptote, I have to follow that vertical asymptote all the way down. I meant to ask for both the x and the y-intercept. What is the y-intercept, Jolie? What's the y-intercept? Yep, where do I touch the y-axis? I don't. There's none. Trick play. How about the x-intercept, Leah? Where do I touch the x-axis?
Is it 1, 0?
Exactly, 1, 0. Perfect. Ooh, tricky trick. Ariella, end behavior. What's the left end behavior? Because as x goes to -infinity, so we're talking about way over here. It literally doesn't exist, right? Does not exist / you could just write like not applicable because it doesn't make sense. We don't even have a function written to the left side. What the heck is going on here? You could say it doesn't exist because it doesn't, right? The whole left side of our graph, we can't have negative x values. And then that's, what's the right end limit as we're going to infinity, Daniel? Positive infinity, and where is it continuous? 0 to infinity. That's it. So that's where we'll stop for today.